If you supply 1850 joules of heat to 2.25 moles of an ideal diatomic gas initially at 10 degrees Celsius in a perfectly rigid container, what will be the final temperature of the gas? B. Suppose the gas in the container were an ideal monatomic gas instead. How much heat would you need to add to produce the same temperature change? And C. Sketch a PV diagram of these processes. Okay, so these kind of problems gives us information about the heat and then also like the mole, and then it asks for like the change in the temperature in order to find the final temperature, right? Then we need to know the change in the temperature. So do we have any like equation that will relate the change in the temperature with the heat and with the mole? Yes, we have. So I guess that this equation Q equals mc delta T is very familiar, right? But instead of having the specific heat capacity, which like represent for like the amount of heat required to heat a substance up by a degree, that related to like each kilograms. Now we just have each mole. That's why we have another heat capacity, which is a molar heat capacity, and that would help to change the internal energy of the substance, and here that's the amount of gas. So here this is a perfect rigid container, so then the volume will be a constant. And it's a constant, then we will have the molar heat capacity for the gas kind of different between a monatomic gas and a diatomic gas to be like 3.3 half of the R or like 5 half of the R, with R as the ideal gas constant with this value. So in order to solve for the delta T, we can just use this equation and apply using this correct appropriate CV for the diatomic gas, which is 5 half of the R, and then just like solve for the delta T. So we just have the Q divided by this whole terms here, and just plug in the values here. Make sure that you have the unit match. So because we have the Q in joule, that's why we need to use the ideal gas constant that measure in joule, which is this value, and then we find the delta T to be this much Kelvin. So here again, just a reminder, change in temperature, change in Kelvin will just be the same change in Celsius, right? Thanks to the conversion bit from Celsius to Kelvin. Change in Kelvin is the same in change in the Celsius, but even though the Kelvin and the Celsius are different from each other, but the change are the same, okay? That's why if it's like 39.6 change in Kelvin, that should be also the same 39.6 change in Celsius. And that's why we got the final temperature to be around this much. So we can have the conclusion that this one around 49.6 degrees Celsius, or you can just like convert to Kelvin if you want. That's for the first question. For the second question, it's just the same mechanism, right? Just the same equation, but this time we have to change the CV for the monatomic gas to be this value, 3 half of the R constant, and then here we use the change in the measure that we found in question A, and then we can find that the heat around this value. Okay. And then for the last question, they asked to sketch a PV diagram. So this is a constant V, right, through the whole process. And we know that by the ideal gas constant, that's PV equals nRT, or we can just move T to the other side, and would be PV over T equals to nR. And we know that the molecules doesn't change the number, the amount of the gas doesn't change because it's a perfect rigid container. That's why this one just equals to constant. And now if you just have V as a constant itself, then the ratio can be simplified as just that the ratio of the P1 over T1 equals to P2 over T2, right? And then if we move the P a little bit, the P1 to the other side, T2 to the other side, then we got this ratio as well, which just tells us that the pressure will proportional to the temperature. Okay, so if we have the temperature increasing, okay, then the pressure also should be increasing at the same rate. That's why we know that for P1 it should be like less than P2 because we have the temperature increasing as the gas being heated up. That's why in the PV diagram it's just simply a straight line like this. Okay, sounds good. Okay, please let me know if you have any questions in the comments below. I really appreciate it. Thank you. Good luck.